Welcome to the NPTEL online course on Fractal and Multifractal. In the last lecture, we have discussed the influence of vertical scaling factor of fractal interpolation function. So, in which we have discussed two different type of vertical scaling factor. One is variable vertical scaling factor, another one is constant vertical scaling factor. So, we have compared both the scaling factor by some examples. So, in this class we are going to discuss the iteration process of the interpolation function. As we know, the fractal usually generated by the iterated process. Cantor set, Van Koch curve and Sierpinski triangle all are generated by taking the initial set and operating the initial set in some logic and using appropriate function, we are generating all the fractals. So, here in the fractal also, whenever you are doing the iteration more and more, we will get the proper and finer approximation. So, in this lecture we are going to discuss the iteration process on fractal interpolation functions. Let me explain. So, in this class we are going to see the iteration process in fractal interpolation functions. Okay. So, you can consider there are xi, consider the data xi and yi belongs to r power 2 such that there are n number of data points are given. Consider these data points. These data points are given to us. So, here we have n number of data points. Maybe this process we can take n plus 1 data points. Okay, let me take the n number of data points. Then in interpolation process, increase the number of data points within the prescribed domain while determining the continuous function to interpolate the known data. In the case of fractal interpolation, the new data point generation specifically depends on the iteration. See, here we will start from here. So, here xi and yi is given, there are k plus 1 number of data, that means I belongs to n of k plus 1. The k plus number of data are given here. As you know, for generating fractal interpolation function by using these mappings li aix plus bi and fi of x comma y equal to alpha I times y plus we need qi of x. The qi may be any function, whether it is a affine or non-affine function. Now, you can observe that given k plus number of data points, the first iteration, in the first iteration, the function, the homeomorphism ln yield k plus 1 point in each of the sub interval. How it works? You can say, if this data points is given, even starting from x1, x2, here we have xi, here we have xi plus 1 and here we have xk and here xk plus 1. If the k plus 1 number of data points are given, maybe it is equal interval or unequal interval, does not matter. Consider there are k plus 1 data points are given here. Then the li, we need how many li's? Li is function from I to ii, where I belongs to nk. That means we need the each interval, we need one L. So, we have a k plus 1 data point, therefore, we have a k number of interval. So, in each interval, for each interval we need corresponding Li. So, we have totally k number of Li mappings. Okay. Usually this Li, if you are taking L1 is function from I to I1 such that this L1 is first of all contraction. So, what is I here? So, I is closed interval x1 to xn and I1 is x1 to x2. x1 to this is k plus 1, right. We have the k plus 1 number of data, fine. This L1 is a function from I to I1. That means this function is contraction as well as the homeomorphism. That means we can find the 1 1 onto as well as bijection between these two mapping. There exists a function f, this Li, we can find this L1, this L1 is continuous and the inverse exists, inverse also continuous, also bijection, and that means this whole interval will be mapped on here. So, the form of this L1 is L1 of x equal to A1x plus B1. This is the contraction factor of L1 mapping. So, this A1 contract this interval so that this whole interval will be mapped to here, plus if you are taking the B1 shift, then this one exactly match with this one. That means if you are applying L1 of I, which is contained in I1, also for this L1 will satisfying the endpoint condition L1 of x1 equal to x1, because this is the x1, and L1 of xk plus 1 which is equal to x2. That means this point will map to here and xk plus 1 will map to x2. This will comes to here and this point will map to here. Then remaining points are in between these two interval. So, we are started with the k plus 1 number of points. So, n points are here. So, totally if you are removing this one, so inside this interval this L1 remaining, if we are started with the x1, x2, xn k plus 1 and corresponding y1, y2, yk plus 1 numbers. Now, x1 is here and k plus 1 is here. You can remove the 2 element from k plus 1, you can remove the 2 element, the 2 element is x1 and xk plus 1. Therefore, we have remaining k minus 1 number of data will be in the inside this interval. So, in the first iteration, if you are doing this L1 on I, this L1 map k minus 1 number of map inside this subinterval. Similarly, this L2 map is a mapping from I to I2. Maybe I will pronounce as L2 is a function from the whole interval to the subinterval I2. Then this same like this L1, L2, if you are applying the L2 map, maybe I will write it here. If you are applying L2 on x2 to x3, the image of x1 xk plus 1 is a subset of I2 which is equal to x2 to x3. Observe that under this mapping L2, this x1 will goes to the point x2 and xk plus 1 will goes to the point kx3. The remaining k minus 1 number of point will be in the between x2 and x3. Similarly, if you are applying L3 function on I, it will maps two endpoint in the x3 to x4, remaining k minus 1 number of points in between. So totally we have k number of intervals. In each interval we have the k number of interval. In each interval there are k minus 1 number of points will be generated by the map Li. So after the first iteration, in each sub interval we have k times k minus 1 number of points, plus you can calculate the n points plus k plus 1 number of points. So which is equal to k square minus k plus 1. You can remove this 2, we will get the k square plus 1 number of point. So now after the first iteration, as a result, at the end of first iteration, the k square plus 1 number of new points are generated. Now in the second iteration, now we have this k square plus 1 number of data points. Now we are going to apply the map Li on each k square plus 1 number of data points. Then in that case, there are then each Li will generate k, there are k subinterval, then not a k subinterval, k square plus 1 number of points, therefore k square number of subinterval in each the mapping will act, therefore the k times k square minus 1 plus k plus 1. Therefore one can get k power 3 plus 1 distinct point are generated after the second iteration. Here k square plus 1 number of new data, here k square plus 1 number of new data after second iteration. So if you are continuing this process, after the nth iteration, the fractal interpolation function generate k power n plus 1 number of new data point after the nth iteration. So see, here we are discussing only on the map Li acting on the x axis. So it generating k power n plus 1 number of new data. So whenever Li generating one new point, obviously corresponding to the Li, Fi generate the same number of point. So if you are calculating in the x direction how many new points are generating, similarly the same number of points will be generated in the y axis. So we can calculate only in the Li direction. So after the nth iteration, this many k power n plus 1 new data points will be generated. Now this will be explained through this figure. Now see, we are starting from the data point. Here the first step, we are started from x1, x2, x3, this is xk and xk plus 1. That means the k plus 1 number of points, it is a given, so that it is a 0 iteration. Corresponding to k plus 1 number of data points, x values, we have the corresponding y values that we denoted here, x1 y1, x2 y2, x3 y3. This is yk associated with xk and xk plus 1 and yk plus 1. Now these data points are given. Now in the first iteration, after the first step, in the step 2, that means in the first iteration, the homeomorphism Ln generate k minus 1 point in each of the k sub interval. Total new points are k square plus 1. That means here the blue dot denotes the old point, that means the given point in the previous iteration. So this is the points given in the previous iterations. Now in each interval, the new point, after the first iteration, there are k minus 1 number of points will be generated. Then similarly, each subinterval produce k minus 1 new point in how many number of interval we get. In that interval, if we have the k minus 1 number of new points, then it will create the different subinterval. In each interval, it will produce the k minus 1 number of points. That means, after the second iteration, one can get k power 3 plus 1 number of data point. Then after the nth iteration, we have this number of data point. You can see this is the starting from the given point. Then after the first iteration, the point generation is given here. The points are very close. For here graphical representation, we can give only few points. Maybe in the next example, we will detailedly discuss. Then here, after second iteration, you can see the curves are more dense. After nth iteration, you will get like the curve like this one. The number of points growth exponential. It will like exponential growth. So here old point, the red is denoted the new point in the first iteration, second iteration, and this one purple is denoted as the nth iteration. Now, if you are increasing the k tends to infinity, then this process will generate the fractal interpolation curve like this one. Whenever the iteration, not a k, whenever the n tends to infinity, the number of iteration tends to infinity, one can get the fractal curve like this one. So, in this way we can construct the fractal interpolation function. For in the computer programming, we cannot go with the infinite number of iteration. Now, whatever the figures which we discussed in the previous classes, we have here the number of points is 1, 2, 3, 4, 5. There are 5 data points are given. We have taken only the after 10th iteration, the graphical representation of fractal interpolation function is given here. This one just a stationary point. Whenever you are keep on increasing the iteration, you will get the more finer structures. Now, I can explain with some simple example. The iteration process shows the magnitude of the data set maximized with the every successive iteration on affine transformation. Now, we can take k equal to 3. That means k plus 1 data points are given to us. That means 1, 2, 3, 4 data points are given here. Then after the first iteration, that means the 4 data points are given. So, the linear fractal interpolation function generated, you can take any fractal interpolation function of the form Li of x equal to Aix plus Bi and Fi of x comma y equal to alpha I times y plus Qi of x. Whether you are taking the linear or non-affine function or quadratic function or alpha fractal function or any other fractal interpolation function, this iteration generate the new points based on these functions. So, it never affect the parameter, never affect the number of points is generating. It is depends only on the number of data points, not on the parameters. The linear fractal interpolation passing through the given data with the vertical scaling factor. Also, if you are choosing the variable scaling also, it never affect the number of point generating. Alpha equal to 0.5, 0.4 and 0.3. So, in each interval we are choosing 3 different, that means alpha 1 as 0.5, alpha 2 as 0.4 and alpha 3 as 0.3, 3 different scalings. Then after the first and second and third iteration, what will happen? So, we have taken 4 data points and the linear fractal interpolation generated for this one, the alpha is given, data points is given, so that we can find the linear interpolation function by using this Cix plus di. If you are choosing Qi as this one, then we can get the corresponding iterated function system. That iterated function system will generate the fractal interpolation function. Now, let us see in each iteration how the iterated function system is generating the fractal functions, that means the points. Now, here we are taking k plus 1 is 4. So, that means k is 3. So, after the first iteration, k square plus 1, that means 3 power 2 plus 1 number of points, totally 10 points will be generated, and at the end of the second iteration we will get k square plus 1 number of data, k square after the first iteration, k square number of data point, here k power 3 plus 1 number of data points. So, 27 plus 1 28, it is not k2, it is k3. Then you can see this is the data point. What is the interpolation data here given? It is given here 0, 0.35, 0.7 and 1. It is the unequal interval data points we are taking, and the constant scaling in the first interval 0.5, second interval 0.4 and 0.3. Now, in the first iteration, after the this is the data point is given here, maybe I will use a different color. Now, this is the data points given here, sorry, not this one, here the blue dots are the given data points. Fine. Now, in this interval we have fixed the scaling as alpha 1 as 0.5, in this interval alpha as 0.4, and in this interval 0.3 up to here and up to here. Now, if you are applying L1, L2, L3 corresponding with this, the L1, L2, L3, it depends on AI and BI only. So, in this L1 generate 2 new points as well as this end point. That means this data will goes to here, right? We are with 1.05, not with 1. This 1.05 will map to not 1. This 1.05 will goes to here, and this 0 goes to 0, and remaining point this point, this one will goes to inside. There will be a 2, 1 to this point, and this point will go inside. So, 0.4 and this point will goes to inside, that is shown here. So, these 2 red lines are the newly generated points after the first iteration. Similarly, if you are applying the L2 on this whole interval, this function will come to here, so that there is a red dot here, we cannot distinguish here, there is a red dot. If you are applying L2 on here, then this point will come to here, then you can get the data point here, then this will goes to here, and this point is moved to here. Now, L3 acting on this same 0 to 1.0.5, then L3 maps this function to here, and this 1.0 to 1.05, here it will maps the same. So, there is a 2 more points will be given. So, after the end of the first iteration, we have initially we started with 1, 2, 3, 4 number of data. Now, after the first iteration, what is happening? You can see 1, 2, 3, 4, 5, 6 number of data. Also, there is a red dot given here, you can just observe here 1, 2, 3, 4 points are generated. So, 6 plus 4, totally we have 10 points. So, after the first iteration, there is a 10 point is generated by the linear fractal interpolation function. You can observe here, there is a 10 point. Now, you can see these red dots are the point generated after the first iteration. Now, we are doing the second iteration. You can observe in the each these 2 interval, now we have 1, 2, 3, 4, 5, 6, 7, 8, 9. All this interval, all the 9 interval, we have the sub interval 1, 2, 3, 1, 2, 3. In each interval, we are going to apply L1, L2, L3. Now, we need to apply L1 here, L2 here, L3 here, and similarly L1, L2, L3 we need to apply. So, in each sub interval, here if you are observing the red to blue, there are 2 black dots. In the each black dot, there are 3 gaps. So, in the each 3 subinterval we need to apply L1, L2, L3. So, it will generate 2 new points. Now, you can count the number of points 1, we can count the dotted blocked lines 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18 number of points, and observe that the blue lines 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means while counting the blue also we need to count the red lines. So, totally 10. So, we can get 28 number of points generated after the second iterations. So, here these 2 images depict the how the interpolation process, how the iteration process are happening is explained in these 2 figures. Now, you can observe that all this interval we are applying the scaling factor alpha 1 as 0.5, and here throughout this region 0.4 and here 0.3. Now, this whole interval is reduced to this interval. For example, particularly this interval, now after the first iteration it is reduced here. Now, here L1 we are applying, L2 applying, L3 applying, here L1, L2, L3. So, now if you are applying L1 here, this interval is reduced to like this one. If after applying L2, this interval is reduced to like here. After applying L3, it is reduced to here. Now, in this image we are giving the straight line as same, but with respect to the scaling factor alpha 1, alpha 2, alpha 3, the vertical scaling will vary, whereas here we are depicted the number of points alone, not in the vertical scaling factor. Now, these 2 graphs just explaining the how many points are generating after the nth iteration, whereas the corresponding fractal function you can observe here. The magenta one is the corresponding fractal function. Here this interval it is smooth, you can see, observe. Now, you can see here it is coming here to here, whereas you can observe this function is how it is behaving, this interval. So, this whole interval it is coming here and increasing and decreasing. So, this straight line, the same pattern is compressed here and we are getting these dots, then increasing and again decreasing. Similarly, if you are considering this one, you can see with respect to the scaling how it is behaved, this interval, straight line, increasing, straight line. And also now you can consider here this interval, in this interval 3 scalings are applied, the scaling is applied and the data points are like this one. So, like that the fractal curves are generated and corresponding the data points are we are generating. So, with respect to the alpha, the vertical scaling, the vertical line ratio will be reduced. That means the alpha controls the vertical direction corresponding to the number of data points are generated in the y directions. So, now one can understand the iteration process of the fractal interpolation function by this figure. So, now one can understand the iteration process of the fractal interpolation through this figure. Thank you. One can refer this book for further details. Thank you.